How many of you are doing Kubernetes today? All right, it's a few of you. And are you using operators, or are you doing deployments? Are you doing the container deployment? What kind of things are you doing today?
Yeah, deployments, yeah.
Some deployments, some microservices, perhaps?
Yeah.
Yeah? All right. Yeah. So one of the typical things that we see in technology, and I think it was very visible in the presentation of Jeff, and things start like replicated, is that every useful thing that we find in technology, we start adopting it, and it starts replicating itself. And once it starts replicating, we need to keep control, and we need to find new abstractions to gain the best of it. And Kubernetes is very hot today. The containerizing applications is like the new way of packaging everything and delivering it to somebody else for running them, for operating, for getting things from development to testing to production in a reproducible way. And once we reach a limit where we have those many containers around, then we need to find ways of getting control of that and automate some of the things. What I want to present to you today is pattern. It's a way of implementing that control, keeping that chaos limited, and trying to get grips of the growing ecosystem of applications, of containers in your own environment, and give you some tools and some ideas on how to maybe implement and get better at running those applications and running them from development to test on this cycle up to production. That's the idea I want to bring to you today. I hope that by the end of this presentation, you get out of the door and you think, oh, that's a cool way, and tomorrow maybe I can find ways of how to implement that in my day-to-day job. I am Gerard Maas. I am principal engineer for Lightbend. I specialize in Spark. I'm the author of this book. It was out last month. It's a huge relief, and today you can leave with this copy here. I brought one for you. One lucky you that I will give out at the end of the presentation, so pay attention. I'll be asking questions. And I've been in the Scala and mostly in the Spark community for a while now. I was an early adopter of Spark. Well, people were not yet talking about it. We were running the Spark 0.9. And from there, I've been more moving into the streaming side of things. So applying Spark, applying Kafka. Now we are getting into Flink as well. I try to see how the same patterns can be implemented in different backends. And I work for Lightbend. Many of you that are here may know the company. We are the company behind Scala. We maintain the Scala project, and we pay the developers that work in the Scala day-to-day. We also have some other cool open source projects. Akka, Play, and Labom come to mind. I really like Akka a lot. And we also create products internally that can be deployed at companies. So we package this into what's called the Lightbend platform, where we have then the open source and the application development for reactive and for microservices, and then more the data-oriented part of that platform. And there is where I work on. I work on the data-oriented side of things. And we are basing all this on cloud technology, on cloud native, and we are putting that, of course, on Kubernetes, because Kubernetes is like becoming the reference to deploy things on-prem or on any of the cloud providers out there. And then I come back to my little box. And I guess that box could represent a container. And I think Jeff is going to laugh because I'm going to repeat his pattern in a second. The containers, they give us three important properties. They give us a way of packaging things, self-contained, so you can take a container and run it somewhere. It's immutable. Once a container has been created, you have a file there, the typical Docker file that says how that container is built. Then you can reproduce it every time, and this is very important. You should do this. It's a single responsibility principle for containers. They should just run one process. They are in charge of use one thing, like microservices are also meant to. And once you have this container idea running there, then you say, oh, that's really cool, but I can take that application from this department and also containerize and deploy it. And so it starts growing. Once it starts growing, you start to have headaches. And especially your operation people start to have headaches because some of those applications are running containers might break down. You want to scale up things. Some part of the business is picking up, and you want to really tune your scalability to some of those areas. And Kubernetes gives you then the means to do that. Kubernetes has a number of built-in functions and like native capabilities that will let you take a container and deploy it as deployment, so nothing can kill it. If a container is dead, Kubernetes will say, oh, let's spawn another container here in this executor here. Oh, I am running up to my capacity. Okay, let's spin another instance of that application and have a load balancer then distribute some of that application load to that new container that has been spun out. And when we start doing this, and it starts getting really exciting. Oh, we have new ways of addressing those problems we would have before. Like, oh, how do I do scalability? How do I do 24/7? How do I keep my applications alive all the time? And Kubernetes is giving us those tools to do it. Up to level, yeah? And it's kind of commonly said, Kubernetes is great when you have like stateless applications that you can replicate, multiply easily. When it comes to state and it comes to resources, then the story is different. You start having some additional complexity. Let's say that you need some storage attached to your application, or that you need to deploy a stateful service like a database, like a message broker on Kubernetes. Then that deployment concept that works very, very good, nicely for give me one container and I can multiply it and I can route data to it, it doesn't work that well. You need additional functionality. And that additional functionality has been, in the past, has been patched into it, maybe like sidecar containers, combining stateful sets with deployment, and a number of mixes that make those deployments kind of complex. But then people from CoreOS came up with this great idea: why not allow extension of Kubernetes? Instead of having these fixed sets of functions on Kubernetes, let's give the people the means to extend the functionality of Kubernetes to add any other function, any other capability that they require. And that's the operator framework, the operator pattern. The operator pattern is a way of extending the way that Kubernetes functions. It gives you means to, it gives Kubernetes means to understand new ways of deploying applications, new ways of operating applications by using the same principle, by observing what has been deployed, by evaluating what was required from me with what is deployed when it's available already, and then calculate any deltas and afterwards. Let's say I need some storage, or I need a new topic in my Kafka, and or some partitioning, and I see, one of my nodes went down, so that operator will receive some events from Kubernetes and will say, I am missing something, I have a mismatch here from what I need and what I have, and then you can act on it and turn over again. Operators are controllers, so they are code that you deploy on Kubernetes. They are code against an API, and they will receive messages, they will receive events from Kubernetes, process them using your specific business logic or using your specific application logic, and then do something. They let you code the knowledge that your operations have about your application, and that's the power of it. It's not anymore about the deployment, it's about the deployment of my business. It's about the deployment of the different components that are making my application beat and serve to my users every day. It's not about a single website, it's about the website, the Kafka brokers, and the databases behind it, because you can code into that operator the things that you require to make your application be alive. There are many operators available. If you see a common pattern among all these operator implementations, is that they are not simple applications, are not things that are easy to manage, easy to scale up. And let's take, for example, Cassandra. If you have ever managed a Cassandra cluster, you know that you need to define some seeds, you know that you need to drain things, so you need to bring a node down. And your operational people will know that. When you want to automate this, you need to code that knowledge somewhere, and the operator is the right place to do that. The operator, it's not that somebody has to be behind a deployment and say, oh, if my deployment goes down, then I need really to act on it and bring the pagers and wake up somebody. No, the operator will have that knowledge coded and say, okay, I have to bring a new node. Well, I will have to drain something, and I will have to then make sure that the ring is balanced again. Today, I am going to give you some examples of how this works. And I have chosen the Spark and Kafka to work out a small example, show you how that is working, what the power of it is, and how it can be used. And of course, we're going to do this in Scala, because we're in the Scala meetup. I'm going to do something quite simple. I will develop two components, a sender and a receiver, but they are sending and receiving. It's not very important, but one of them will be generating data, then I will have a Kafka topic, and all the data goes to the Kafka topic, and the other, at the other side, the receiver will take the data out and print it out. It's a simple scenario, but then I think it will illustrate for you and create some intuition about how this operator thingy is all working together. So I have here my Spark sender, and I have a Kubernetes cluster. Let me just open things up. I don't think this is visible in any way. Jesus. I think I'll have to, oh, there, okay. So, yeah, the resolution is terrible, but we don't need to see this structure. We just need to see the codes. Okay. So I have a, no, it's too big. All right, can we read this? Yeah, okay. This is a bare bones Spark application using a structured stream. I am creating an in-memory data generation, and that is this rate stream that is created here. This has a rate, it's all coded there, so it will be creating 10 events per second. And I am going to create some users using some random functions. I'm going to create a user ID for every one of those events that I'm creating in memory. And then I will have my ID of the user and the user structure be sent to, let me just take all this space out so we can see the structure of it. So I have a structure with the ID, with the times type and the rate. That is, let's say, users are doing something on a website and I create some data stream out of it. And I'm going to immediately write this to Kafka. If I want to deploy this, I need a few things. I need a cluster, I need resources like nodes to run my Spark application. How many of you have run Spark applications before? Right, quite a few people. So I guess you're familiar with the Spark submit and all the process that comes with it. The first thing we need to do is to create a package for it. So I have some build already prepared, and that build, what I'm going to do is I'm going to create the jar file, but I'm also going to create a Docker image already. And so I am doing two things at the same time. I take the jar file that I created from that small job there, and then I also create a Docker image out of it. Before I proceed, I need something else. So I said I have my Spark applications, but I need to connect them with Kafka. And I need my topic to be there. So usually you also use a kind of CLI and API to create topics in Kafka. But using operators, we do this the Kubernetes way. We do this in a declarative way. I have here a user's topic file. So if we see, or let's call it the user's topic file there. And this user topic file is describing topic. It's not saying how somebody needs to go in the CLI, install some binaries and connect to a Kafka cluster. It doesn't say any of that. It just says that I need, in some namespace, I need a topic with this name, with some configuration, so many partitions and so many replicas. That's an intention. It's a declaration of something that I want. And once I have declared this, I can say to Kubernetes, well, make it so. And I can say kubectl apply, and sorry, I have one letter too much. All right, well, I have created it already, and I did not delete it, just for a simple reason it takes some time. But it's there. And then we can say kubectl Kafka topics, and we can list all the topics that are available on my cluster right now, including the user topic that is there. If we wanted the more details about the specific user topic, then we can say, give me more information. The user's topic. Okay, so I had an intention, and here I have an implementation of it. I have a reply that says this is what I have made out of it. It has done the only one replica and 3 partitions, and it's having some additional information for me. So now I have my topic available there, and I can start deploying my application in Spark. So let's go with Spark Sender here. I have done my build. Let's do the publish. The publish, what it's going to do is to send my Docker image to some Docker repository, and let me get out of there. And I'm here. This is OpenShift, Red Hat's implementation of Kubernetes. And I am currently in a namespace where I'm going to deploy my application. I'm going to open it first so we can see the effect of deploying things. All right, so I can deploy something. And the deployment is also based on a YAML file. Let's see here my YAML, Spark Sender. All right. I'm saying here that I want to deploy an image that I just published on that Docker repository. It has a main class, that is the class I implemented. Here's where you are going to find the jar file. The jar file is in the Docker image, so it's local to the space where it's running. Oops. And it needs some security constraints, so we have their service account resources, limits, and allocations, and the number of executors that it should be starting when that application starts. So we should be seeing one executor running if everything went fine, and there we have one executor. We have my first Spark application running. All right, that was not very painful, except that I spent almost the whole day yesterday trying to figure out how that works. And well, an important thing here, if you have been working with Spark before, is that you see the difference of being declarative and packaging and developing, sorry, packaging and deploying things versus having to have everything on your own laptop. Separation is stronger. You can develop things and test things, but then when it's done, you just say, okay, this is the Docker image, and the development process, or sorry, the deployment process can start based on that, and can be automated. You don't really need to like throw it across the wall to somebody else. It all can be automated using the CI pipelines. The next thing we want to do is to have a receiver. So we have an end-to-end application running there. Same thing, the receiver, it's pretty similar to the sender. So let's open it up. I'm using the same classes. All right, so I declare a case class here that is the same as I've been sending through JSON in the past from the sender. I obtain the schema from that case class, and then I do the little dance of the streaming declaration. So I am going to read from Kafka. I give the address of the Kafka brokers. I have some issues with the mic. Is all okay there? Yeah, okay. And once I have read the data, I'm going to say, okay, this is a string. I have a schema. The schema I extract from the case class declaration. Sorry, I think it's gone too far up. There. So I have my case class, and I call this incantation from Spark to obtain the schema from the case class. And once I have that, I can then just print it out on the console. Okay, so I'm going to get the data back from Kafka, and I'm just going to dump it into the console to see that things are working end to end. Right, and let's get my, well, no, and this one. Okay, so I build stuff. All right, first SVT stage, prepares, compiles everything, puts it in a directory. How many of you that were doing Spark were doing these fat jars or assemblies? You'll be happy to know that Docker images are the new assembly files. So there's no need, especially for that process of cleaning up the assembly and doing the duplication. It's always so error prone, and you know what you're throwing out with those general rules. You just need to copy things on that predefined Docker image. Okay, so I publish stuff, and then I am going to deploy things. And if everything goes well, I should see my second deployment here. I have the driver starting up, and I could do some logs. Let's see. We have some stuff up there. We have typical Spark running. What's going on here is that I am telling the Spark operator, here is a specification of a Spark application, here is a Docker image. Take the Docker image and instantiate a Spark application out of it. All right? And the Spark operator takes care of taking that application, talking with the Kubernetes cluster, allocating resources for the first stage, for the driver part, and then initiating the deployment of your Spark application. In the second or something, we should start seeing the macro batch process. So we have the first batch there, and we have data. All right, it's always happy to see things are running like you expect. Okay, so we have data flowing from point A to point B right now. Yeah, we have developed a streaming application with a sender, receiver, and a Kafka topic in between, using Docker containers and using a declarative approach of saying, this is my YAML file and this is how you deploy things. I didn't have to go to Spark, to the Spark submit and start typing very long incantations of scripts. It's all very self-contained, I would say, and very declarative. But, so there are two elements to that. There is to create that operator, there is a definition. There is that definition of what you can do to deploy, or how you can describe a resource for Kubernetes. So let's see kubectl get CRDs. We have there a number of CRDs installed, and I think one of the most straightforward ones is a Kafka topics CRD. The CRD is a description. Let me in JSON format. A CRD is a description And that description says what I can accept. How can you give me a resource that I can understand? This is not like that Kafka topic description I showed you that had a name and had a topic number or topic name, and it had a number of resources and configuration attached to that. This is actually, how do I describe that? I need something that have a topic list. I need something that has a number of partitions, that has a number of replicas, that has a given topic name. This is a CRD. A CRD is installed in Kubernetes, and the combination of the CRD with the controller is what the operator, this custom operator is on Kubernetes. That gives you the power of extending Kubernetes functionality to do whatever you want. And as you saw, there are many of them already available. To give you an idea how that works, when we submit a job like we just did in Spark, we submit a YAML file. The YAML file, the submission, it goes, of course, to the Kubernetes API. The Kubernetes API says, oh, this is registered to this controller. It goes to the controller, and the controller is going to do its own thing. From here, it's your own business. From here, it's you who is in control. In the case of Spark, and it's something that somebody else did, what they are doing is they are taking the YAML file and they are translating all those parameters that are in the YAML file in something that can be used for Spark Submit. And it does in Spark Submit using the Kubernetes support in Spark that then instantiates a driver, and the driver then instantiates its executors. It's also a cascade responsibility. So the responsibility of the operator is launching the Spark driver, the Spark job, and the responsibility of the Spark job is to launch its own workers. This is a pattern that we can replicate, and this is exactly what I want to share with you today. So we saw two things. We saw that I was using the Spark operator to deploy my Spark application. We see that the Spark operator then delegates to the Spark driver that is responsible for deploying the executors, and the topic operator is responsible for deploying the Kafka topics. I still have to do some work here. I still have to put all those pieces together. And then the idea is to have your own operator that takes the pieces that are required to create your own application, to realize your target, and code it in the operator where you define your own CRDs, and you find your own way of deploying applications to Kubernetes. And I would like to show you how are we using this pattern to actually turn Kubernetes into a streaming platform. And this is the project where I'm working on, and it's split in actually 4 parts. The first part is how you develop. There is an SBT plugin that understands the code that you're writing, the Spark code. We also support Akka streams, and we're working on Flink. And we define something that's called a blueprint. Is a way you connect things together. So instead of having that knowledge somewhere else outside of your application, we are putting that knowledge inside the application. And we have a CLI. In Kubernetes, you can also extend Kubernetes at the client side by providing plugins. So we have developed a plugin for Spark, for kubectl. It's called Pipelines, and we have a UI. I will give you a glimpse of it. Then on the Kubernetes side, we have this custom operator that is coordinating the work of 3 different sub-operators, or what I call operator federation. We are taking the capabilities of the streams operator, the Spark operator, and the Kafka operator to create end-to-end streaming applications. So you code your streaming application, you say how that thing gets connected together, and we give that information to the operator, to the custom operator, to then realize the runtime to get that pipeline running from end to end. And then just to compare the approach, let me show you how that works using this custom operator. And I have a project somewhere here. Boom. All right. In my project, I'm going to do exactly the same, but I have a new component. So I have something that is generating data, very similar to the previous one, something that is capturing the data, but I have a new element here, and that new element is a blueprint. And the blueprint is saying, how do I connect things? I declare an ingress, this is a Scala class. I declare an egress, it's another Scala class. They extend something that we call streamlets, and we are going to say that the output of the ingress is going to be connected to the input of the egress. Instead of having those built shell files that I created, we have then everything integrated in a plugin for SBT, and this build and publish. When I do build and publish, I am actually doing the same process as before. I'm taking all the codes. I am creating a package, first jar files and then the Docker files. And once that's created, is published to a Docker registry. So I am done there. And once I have that Docker image, it was declared here somewhere. There it is, my Docker image. Oh, sorry. Let's Ctrl-C. Okay, I can then use kubectl, kubectl, and then the pipelines, and I can deploy things. And if I'm fast enough, I can come here and see how those components start appearing, if everything went well. So we are using this custom operator approach to provide a way for users to create streaming pipelines end-to-end. You are not then creating every component in isolation and deploying them independently with all the pitfalls that come with it, but we are saying, okay, we know what components you are developing, you create those different elements, you tell us how those are connected, and then we use the power of those different operators to create the connections between them and deploy the whole application there. Then once you have that in place, you can start doing really cool stuff. Like you can, for example, scale up things. What is a scale? A scale is something that you want to do. You can do a scaling up of a microservice. You could do a scaling up of your data processing backend. Typically, those are operations that are done differently depending on the framework that you're using. Sometimes you just have to add pods to a deployment. In other cases, you have to probably redeploy a whole application. With the custom operator, what you can do is to abstract out how that is done and only focus on the operation and the result of the operation. You can say, using this Spark pipeline, and I have one component, and I say I scale it to 5. And once I scale it to 5, well, the operator needs to know this is something that goes for Spark. So I'm going to say I'm going to tell the Spark operator that it needs to apply that scaling up function that typically is to break down the existing components and redeploy with the new scale. Oh, sorry, I did something wrong. There. Okay. And just to this how the thing looks in terms of UI. Then we have their Spark pipeline, and you can see the flow of data going through it. As the producer starts picking up data, then you will see the data going through the system inputs and outputs. But the important thing is the custom operator part of the system. But there is something maybe not completely right. Okay. Let's continue. So we have seen how to combine actually different backends. In this case, we have Spark and we have Kafka, and we have created an application seamlessly using a single definition from a single project and telling the operator what to do with those different components. Few principles that we have applied while developing this is having this blueprint information gives you a holistic view of the application. It gives you also a means to adapt the application very quickly. So for example, I could check out, and this is processor. So I can add new components to it. And the second one is having a schema-driven approach. So one of the points that we are using is to declare the information that goes from one place to the other using Afro schema. So in this case, we have something that's called a record of named data. That's the data that's going to be produced, and the other side has to consume that data. I have now added another element to my pipeline. Before, we didn't have this process, so I have something that is computing statistics on the data that is flowing from A to B. Maybe I forgot to to update something in my pipeline to say, okay, I reconnected all those cables, all those pipes, and I can have the and I can have the SBT plugin actually check the consistency of my complete application. So in this case, I have now this process. It will create some data that is aggregated, and my outputs cannot cope with that data, so it will say, oh sorry, the outlet is not compatible with the data of the inlet. So we are applying the same concept of type safety also to the data that is being sent across Kafka, so we are calling it like data safety. I can quickly go here and change what I need to do, and in this case is of course something very simple. The egress needs to do some aggregated outputs instead of the raw data, and then the whole process should work properly. I will have a new file, and with that new file I can do again a deployment and extend my existing application. There we go. Check. Okay. There, we should then be having a new component joining that pipeline. On the data communication side, the data integration side, what I find very important here is when you have a schema-driven development for data pipelines, you can start thinking of the intermediate steps of it as reusable data. Every time that you have something that you're writing to Kafka in many cases, you can have different consumers to that. And you can start thinking about streaming data the same way you think about files in a file system, something that can be reused for new applications as you develop your business. All right, so we have here now a complete end-to-end application. Now with my egress having some information, some aggregated data. It's still taking some time to start up. Okay, so those are very important design principles that we have put into the design of our custom our custom operator. Three tools that we have developed in this case, an SBT plugin to put everything together, to allow you to write the data, concentrate on your business logic, the CLI to extend the client side of Kubernetes, and the operator, of course, to make all this possible. And then that's the thought I want to leave with you, is that by harnessing the power that existing operators out there, together with the business logic and the knowledge that you have in your own organization, you can then create and crystallize that operational knowledge into custom operators and transform whatever Kubernetes deployment that you have out there into a really custom platform for your business. And that is what I wanted to, that insight that I wanted to share with you. I have some resources here. One of my colleagues, Sean, has done some presentations on how the Kafka Operator works, Streamsy. And once you have the slides, you can go to the resources there. There's a very cool demo that is recorded. We contribute to a Streamsy operator from Red Hat. We contribute to the Spark operator that is run by Google. One of my colleagues, Gerard, also created a presentation and gave it to the folks of Red Hat about how the Spark operator works, and we are currently refactoring a lot of the pieces of the Spark operator to make it more robust. And if you want to read more about what we are doing with pipelines more in the deployment side and how we're working with customers with it, you can have a look there or approach me.